Alrighty, next up we have reaction pathways, also known as reaction mechanisms. Let's do this first. So let's look at something called a heat content diagram or energy diagram. Let me mention a few things. We'll draw some. I'll explain what they are. So it says, remember that the activation energy, or EA, is the minimum amount of energy required for a reaction to occur. It's the energy that must be added to the reactants to ensure that those particles collide hard enough for a chemical reaction to occur. So there's some heat content diagrams in your book on page 548, I believe. Let's take a look there, as well as 552. And so either one of those will be fine to look at. I think we'll start with, it doesn't really matter. We can go to 548 is fine. So I'm going to draw something similar to that's there. So let's set up our axes. So we can put one of several things on the y-axis. It could be heat contents, also known as enthalpy. Symbol for that is H. Your book has energy. I like to put potential energy. So this is a graph showing the change in potential energy that occurs during a chemical reaction. Now, I don't like what your book has there on the x-axis on page 448. Instead, let's put this reaction progress. So the book says time. So I don't know if I want to use time though, especially for what I'm going to show here in a little bit. So reaction progress over the course of the chemical reaction. All right, so we're going to start off with the heat content diagram for an exothermic reaction. Remember, an exothermic process is one that releases energy to the surroundings. Now, something that is very, very, very important is understanding why that happens. So why is energy released to the surroundings? Well, it has to do with this. In an exothermic process, what you end up with, those substances, by the way, are known as the products. What you make or what you end up with have less energy than what you started with. And that difference in energy between what you end up with and what you started with is what is released to the surroundings. So let's take a look here. Let's draw. Here's a typical profile for a heat content diagram for an exothermic reaction. So maybe something like that. So again, on the y-axis, we have some numbers. So this number here, whatever that happens to be, I'm not going to actually use numbers, but that number is the energy of the reactant. So I'm going to label this part of the graph with an R for the reactants. And then if we, I guess we can do this all the way over here. That number here, whatever that is, I'm going to call that the, whoops, not reactants again, but rather the products. So that represents the energy of the products. Something else that we want to label on here is the activation energy. Now think about what I just told you about activation energy. Activation energy is the energy that you must add to the reactants to get them to react, to get them to form products. So activation energy is from here, the energy of the reactants, to the top of what I call this hill. So from the reactants to the top of the hill, that is the activation energy. Now, something else we should label on here as well is something called the delta H. Delta H is the change in heat content or change in energy that occurs during the reaction. And so technically, when we're calculating delta H, especially using this graph, we take the energy of the reactants, energy of the products minus the energies of the reactants. So another way we can think of it is delta H is the difference in energies of the reactants and products. And again, that difference is what is, in this case, released to the surroundings. Now, what do you notice about the values for the energies of the products and the reactants? Well, the products have less energy than the reactants, and so when we plug in some values for these two things, we're going to end up with a negative value. So just know that's the delta H, the change in enthalpy, for an exothermic reaction is negative. Now, it's not really a negative number technically. That negative just tells us that energy is released to the surroundings. Now, let's go ahead and do this. I'm going to add a second curve to this graph. And so go ahead and do that with me, please. We'll draw that in a different color. All right, so what do you notice about the blue curve versus the yellow curve? So first of all, both of them, both curves, they actually represent the same reaction. How do I know that? Well, the energy of the reactants is the same, energy of the products is the same. So because of that too, that means our delta H is the same. What's different? Well, difference we see is here in our activation energy. So I'm going to label it, it doesn't matter where, I guess. I can label it inside. From here to here is the activation energy for that reaction represented by the yellow curve. So the reaction represented by the yellow curve has a smaller activation energy. I think we talked last time about the relationship between activation energy and reaction rate. So a question right there under the graph says, which of the above figures represents a reaction that will occur faster? That'll be the one that has a lower activation energy. The lower the activation energy, the faster the reaction. So that is the only difference between these two reactions. Now, why would the activation energy be lower? What would cause that? A higher temperature? No, I don't think so. If you increase the temperature, that does not change the activation energy. Is there anything that you can think of that changes the activation energy for a reaction? Yeah, that's right, a catalyst. So that yellow curve perhaps is the reaction in the presence of a catalyst. So maybe we should label that. So we'll talk more about it in a little bit, but we'll go ahead and mention it now. And then the blue curve represents the reaction in the absence of a catalyst. And that's, I guess, should not be plural here. And technically, you should say catalyzed, the catalyzed reaction versus the uncatalyzed reaction. Next, let's take a look at the heat content diagram for an endothermic reaction. Let's again go ahead and set up our axes. So again, we have potential energy on the y-axis. I just put reaction because sometimes that's all it's written there. Reaction is on the x-axis. Reaction progress, again, over the course of the reaction. However long it takes, doesn't really matter. All right, endothermic reaction. So what you may recall from an endothermic process is that energy is absorbed from the surroundings. So what happens because of that? Well, in this situation, what you end up with has more energy than what you started with. So you're adding energy to the reactants in order to form the products. And the products then are going to have more energy than the reactants. So let's take a look again this time. Typical profile for an endothermic reaction. Once again, here, again, this is like at the very beginning, time zero, even though it's not time on the x-axis. The very beginning of the reaction, you have only reactants. So again, whatever this number is here represents the energy of the reactants. And I'll keep it blue, I guess, this time. And whatever that number there is the energy of the products. Let's again label, like last time, activation energy. Let's label delta H. And so from here, the energy of the reactants to the top of the hill, I didn't make that in the middle, but that's okay, is our activation energy. And then delta H, again, difference in energies of the reactants and the products. So applying what we said earlier about delta H we calculate by taking the energy of the products minus the energy of the reactants. And in this case, since the products have more energy than the reactants, the sign for delta H will be positive. Always true for an endothermic reaction. Let's take an even closer look at this. Let's go back to this one. Let's look at the blue curve. It doesn't really matter, but we'll look at the blue curve. Let me ask you a couple questions. True or false? And please answer this honestly. True or false? All chemical reactions require energy. Go ahead and answer that. And what did you say? The answer is, of course, true. I kind of get it though. If you said false, it's like, wait a second. How can energy be required if the reaction is exothermic? I thought an exothermic process releases energy. Yes, there is a net release of energy. But again, didn't we talk about this? Activation energy, energy required for a reaction to occur. So all chemical reactions require energy. So that's from, and again, I'll draw it maybe in a different color. From here to here is the total energy required for the reaction to occur. All right, next question. True or false? Again, please answer honestly. All chemical reactions release energy. Go ahead and give your answer. So what is it? All chemical reactions release energy? That answer is true. And again, you might be thinking, wait a second, how is that possible? What if you have an endothermic reaction? Endothermic reactions don't release energy, they require energy. Well, they require a net absorption of energy, but it is true. All chemical reactions release energy. Now let's look on this graph, and again, I'll draw it in red. From where to where represents the total energy released, not net, total energy released. See if you can figure that out. So from here to here is the total energy release, right? We're going from the top of the hill all the way down, all the way down to the products. Now let's look at something. What do you notice about the energy required compared to the energy released? More energy is released than is required. Hopefully that makes sense. If more energy is released than is required, then overall this process will be exothermic. Let's take a look here. Let's use this example, endothermic reaction. True or false? This reaction requires energy. That is true. That's the total amount of energy required. You should label this on your graph. True or false? This reaction releases energy. That is true. From here to here represents the total energy released. What do you notice this time? More energy is required than is released. If more energy is required than is released, then overall that process will be endothermic. Very, very, very important. Now let's do this. Let's compare heat content diagram to kinetic energy distribution curve. So let me set up my axes here. It's going to look a little funky. So let's start here, I guess. And then we'll put this one here next to it. All right, so on the left, we're going to draw a kinetic energy distribution curve, but I'm going to take that and rotate it 90 degrees counterclockwise. So we have, oh, this is going to be hard to label. Number, oops, I don't want red. Let's go back to our blue. Number of particles versus kinetic energy. And here we have potential energy. We're going to put a heat content diagram on the right side versus reaction progress. So let's go ahead and draw that curve. Let's see if I can do that this way. So something like that. Hopefully you can see how I'm doing that. So I just took, like I said, take the kinetic energy distribution curve and rotate it 90 degrees counterclockwise. Might be easier for you to just turn your paper. Unfortunately, I can't turn my board and draw this. Turn your paper and draw your kinetic energy distribution curve like that. And then next to it, let's draw a heat content diagram. Let's go, I don't know, exothermic, I guess, is fine. All right, so here's what I want to do. Again, remember, this is our activation energy. So let's do this. Go all the way over here. And that corresponds to the activation energy on this graph. So if we go over here, I'm going to show that in a different color. So if we just take the energy of the reactant and we go over to here on our kinetic energy distribution curve, the reactants don't have enough energy to react. Remember, they need a certain amount, a minimum amount of energy to react. And so if we look again on our our kinetic energy distribution curve, then this whole area here under the curve represents all the particles that have enough energy to react. If you have this much energy or this much or this much or this much or this much or this much, you don't have enough energy to react. Only when the particles have this much. So what I'm trying to show you here is the relationship between the two graphs. Here's another analogy for you. Let's say you have a boulder right there, and your job is to get that boulder from here to down here. Now, is it just going to do that all by itself? Nope. How are you going to get it down the hill? First thing is you got to get it to here. Well, how do you get it there? You have to move it. Move, motion, energy of motion, kinetic energy. You have to supply enough kinetic energy to that boulder to get it to the top of the hill. Once it gets to the top of the hill, it will roll down to the bottom all by itself. Kind of like chemical reaction. You got to supply enough energy to start the reaction. Once that reaction starts, it will continue to occur all by itself. We'll use some of the aspects of this heat content diagram stuff in this next section here on reaction mechanisms. So kind of mentioned at the very beginning, a reaction mechanism actually shows how the chemical reaction occurs. So let's take a look here. We have a balanced chemical equation for some reaction. This equation does not show how the reaction occurs. It simply just shows what you start off with, so those are reactants, and what you end up with. Those are the products. But it doesn't show you how you go from here to here. That's the job of a mechanism. Let's pretend that it did show you, that this equation does show you how a reaction occurs. Here's what it says. The above equation, it should say there, so let me fix that. The above equation implies that 3 I minus ions, right, there's 3 of them, and 1 C2H4Br2, so that's dibromoethane. Don't worry about the name right now. 1 C2H4Br2 molecule collide at the same time at the right angle, and I don't mean a right angle, the right angle or orientation, and with the right amount of energy. All right, think back to collision theory. What are the chances of 4 particles all colliding at exactly the same time at the correct orientation and with sufficient energy. The chances of this happening are really, 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 really small. In fact, the probability of this happening is so low that it is considered to be impossible. So how does this reaction occur? Reactions appear to actually proceed in a series of steps known as elementary processes, where only two particles collide at any one time. So much higher chance of two particles colliding at the correct angle and with sufficient energy than four particles. How about three particles? That's even rather unlikely. Usually collisions occur between two particles. So let's do this. Let's take a look at a possible mechanism for this reaction. Say possible because reactions can actually occur via different mechanisms. I believe the same process is shown in your book starting on page 556, I believe. I think it's the same thing. So let's take a look. Here are some steps. So in the first step, we have one C2H4Br2 molecule and one I- ion colliding. And they make this. And then in the second step, we have this occur. There's 4 steps total, by the way, if you're thinking about spacing this out. Next step, we have this. And then lastly, we have this. All right, let's do some labeling. This step here is relatively slow. This step is relatively fast. This step is relatively fast. And this step is also relatively fast. That'll be important in just a bit. So let's go ahead and do this. Let's draw a line underneath that last step. Again, these are our steps, our elementary processes. And let's come up with the overall equation. So here's how it works. If you have the same substance on the left side of one equation and the right side of the another equation, they will cancel. So we want to cancel anything that appears on opposite sides of two different equations or two different steps. So what can we get rid of? Well, I see C2H4Br minus on the right side of this equation and on the left side here. So that's going to cancel. I don't know why my pen is not working. Maybe I'll change colors. There we go. I see IBR on the right side here and on the left side here. That cancels. I see BR minus on the right side, BR minus on the right side. That's not going to cancel, so be careful. Anything else cancel? I see I2 on the right and I2 on the left. That cancels. And I think that is it. So anything that's not canceled, bring it down. Let's say we have C2H4Br2 plus 1, 2, 3. All those I minuses are on the left side, so we're going to combine them. 3I minus to make, we have C2H4 plus 1, 2 Br minus plus I3 minus. Now, what do you notice? Yeah, it's exact same as what we have at the top of the page there. So let's fill in some blanks. First of all, each step in a mechanism must proceed on to the next step. So we saw this with the on the first page, the intro to the clock reaction lab procedure. That was a mechanism. It showed the steps involved in that process. Each one continues on to the next. And like we saw here, the sum of all the individual steps will govern the overall equation for the process. And lastly here, very, very, very important. The slowest step in the mechanism governs the rate of the overall process. This slowest step is called the rate determining step. Have you heard the expression, a chain is only as strong as its weakest link? Well, I have a similar expression for reactions. A reaction is only as fast as what? It's only as fast as its slowest step. All right, some vocabulary. Intermediates. An intermediate is an unstable. What does that mean in terms of energy? That means high energy. Unstable, short-lived particle that appears only briefly in a reaction mechanism. So something that you'll need to be able to do is recognize an intermediate in a mechanism. Here's how you do it. It appears as a product first. It's a product in an early step, and it cancels out as a reactant in a later step in the mechanism. It is a short-lived particle that is made by the reactants on their way to forming the products. It, meaning this intermediate, it never appears in the overall equation. It cancels out. So it's never shown. So going back to our mechanism, there are three intermediates. Sometimes these are known as activated complexes. An activated complex technically is made of more than one particle that have been stuck together, whereas an intermediate can be just made of one thing. So all activated complexes are intermediates, but not all intermediates are activated complexes. So be careful with that. So we have three intermediates, C2H4Br minus, IBr, and I2. Each of those substances was a product in an early step and a reactant in a later step. All right, so let's talk some more about these activated complexes or these high energy intermediate particles. So once again, an activated complex is the molecule or particle that forms at the moment of contact between reacting particles. Your book shows this on page 548 on that heat content diagram. So you have the reactants, they collide and momentarily stick together to form this high energy intermediate particle. Let's draw a heat content diagram. Thermic. So again, we got reactants here, products here. How about on this curve? Where on this curve represents the activated complex, this high energy intermediate particle? Right there, top of the hill, as you can see also in the book. Now, something to be careful of is this heat content diagram is for a one-step mechanism. What if you have a multi-step reaction? Well, each step in a mechanism has its own activation energy. So sometimes we get something like this, where this is the activation energy for the first step, and this is the activation energy for the second step. Now I showed them being the same height, but they may or may not have the same value. So just want to show you that we can have multiple activated complexes in a reaction. This can be some sort of intermediate particle here, maybe. And so we'll stick to something simple, though, usually on our heat content diagrams, just this kind of method that's shown on the left here. So let's take a look at what's next. I guess it's so important that we will mention it again. An activated complex is a highly unstable, that means high energy, short-lived particle. All right, kind of already talked about it. Relationship between catalyst and activation energy. It says, remember that a catalyst speeds up a reaction by lowering the required activation energy. Let's once again draw a heat content diagram showing catalyzed and uncatalyzed reactions. A blue curve, this is our uncatalyzed reaction. Catalyzed. And then again, we'll draw a yellow one. Yellow being the catalyzed reaction. Again, talked about this before, only difference is the activation energy. Now I'm going to cheat a little bit. Let's compare heat content diagrams again to kinetic energy distribution curves like we did here. Wherever it is, there it is. And what if we have a catalyst? Well, activation energy is going to be lower. Activation energy is going to be lower. Maybe I should draw this in a different color since I already used yellow on here. Ooh, yellow and red, my least favorite combination of colors. And this whole area under the curve here, past EA, this is red. EA is the EA of the of the catalyzed reaction. It's lower. More particles have enough energy to react. I think we've already been down this road before. All right, just as important it is to be able to recognize and activate a complex in a mechanism, equally important to be able to recognize a catalyst. Now think about what I said about catalysts. A catalyst is something that you add to the reactants. You add it at the beginning of the reaction. That should help you here. A catalyst appears first as a reactant and then later as a product. So kind of the opposite of an activated complex. All right, so I don't know why it's not written here, but you have it in your notes. Go ahead and draw a line under that last step and give the overall equation for the reaction. Identify any intermediates and identify any catalysts. Go ahead and do that now. Pause the video. All right, so it looks like we have 3 intermediates in this mechanism. I is produced in the first step and second step and consumed in the third. Notice anything about the first and second step? They're the same. Can we just combine those and make 2Cu plus 2I minus? No, because what would that show? That would show 4 particles colliding simultaneously. Doesn't happen. So this collision between Cu plus 2 and I minus just happens twice as often as the other collisions. We have CuSO4 plus produced in the 4th step, consumed in the 5th step. And then we have Cu plus 1, like I, also produced in the 1st and 2nd step, and this time consumed in the 4th and 5th step. Catalyst, Cu plus 2. It's a reactant in the 1st step and 2nd step, same step basically. And it is produced in the last step. You put it in the beginning and you get it out at the end. So if we cancel all the intermediates, cancel the catalysts, we end up with this equation. Like I said, if you want to show that the reaction is catalyzed by the copper 2 ion, we can put Cu plus 2 over the arrow. All right, so a lot going on in that lesson. Thanks for hanging in there. Thanks for watching, and we'll talk next time.